Okay, so we have a classical electron on an elliptic orbit in a hydrogen-like atom, and we are supposed to calculate its average distance from the nucleus, and we need to express this average distance in terms of the Coulomb constant, electronic mass, and its energy and the angular momentum. And we are bound to use the equation of orbit for an electron in polar coordinate, and we will use conservation of angular momentum as well. So let's start with the equation of orbit, which is given in terms of alpha and epsilon. Alpha is the lattice rectum and epsilon is the eccentricity, which you can look up in textbook of classical mechanics. Now let's consider the time average of r, which is given upon 1 upon capital T, and the integral of r of t dt from 0 to capital T, where the capital T is the time period. Now we need to convert this integral into in terms of theta. So for that we will use the conservation of angular momentum, and from here we can calculate the expression for dt. So this dt will go into the equation number 2, and from this dt we can calculate the time period, which will also go into the equation number 2. So substituting everything in equation number 2 will yield the average distance of electron from the nucleus in terms of theta. So in the numerator we have the integral which has r raised to power 3, and in the denominator we have the integral which has r raised to power 2. So let's call them I3 and I2. Now let's consider In, that has r raised to power n in the integrand, and after substituting r, which is 1 upon 1 plus epsilon cosine of theta, we get equation number 5. Now we will do the integration in the complex plane, and for that we will consider z equal e raised to power I theta, which is the parametric equation for a unit circle which is centered at the origin, and from here we can easily calculate cosine of theta and d theta, I mean everything in the integrand in terms of the complex numbers. So we will substitute d theta and this number here in equation number 5. So we get In in terms of z. So if we factorize the term in the denominator, because it's quadratic in z, so we can factorize it, and we get something like this, where z plus and z minus are the roots of this equation. And in terms of the complex calculus, we can say that z plus and z minus are the poles of this function of order n. But remember that for the bound orbit, eccentricity is in between 0 and 1, and the expression for z plus and z minus is given by this equation, and since eccentricity is a positive number, so it means that z minus lies outside of the unit circle. So in solving the complex integral we will use the residue theorem, and we will calculate the residue at only z plus, because z minus lies outside of the contour, and we can look up for the formula for the residue of some function at some point, and it turns out to be this. And once we substitute everything, we get I2, which has power r raised to power 2, and we also get I3, which has r raised to power 3. So now the average distance of electron from the nucleus, which was I3 upon I2, is turned out to be alpha upon 2 multiplied by 2 plus epsilon square divided by 1 minus epsilon square, where alpha is this, n square upon nk, and epsilon is 1 plus 2 e l square upon nk square. One important thing to note is that the energy of the electron is negative, so the first term is essentially a positive quantity here. So this equation number 10 is basically a positive number. And the other important thing is that if we substitute energy and the angular momentum from quantum mechanics, this average distance from nucleus turns out exactly the same as we do in quantum mechanics. So there is a nice correspondence in classical mechanics and quantum mechanics, which is nice. Thank you.